Hi, I'm Olivia, everyone's favorite math teacher. And in this video, we're going to learn principles that help us avoid errors when we are applying the rules that we learned in the last video. We're also going to practice applying those rules and see how those principles aid us. So now that you've gotten to see some of the formulas that we use in order to make it a little faster to take a derivative, you've probably also seen how it can get a little complicated with some of the algebra. So what we're going to talk about are some of the problem prevention principles, try to say that 3 times fast, that will help you prevent errors while you're working through your calculus. First thing is organize your work. That should be pretty obvious when we're talking about homework or tests, but some things you may not think about are you should organize your scratch work. What I mean by that is section off whatever the paper is that you're going to be using to jot down notes or do the work that's not going to be on your test or homework sheet, and then only work on a problem in that section. So for example, problem 1, put a square, do your work in square 1, and then do your work for problem 2 in square 2. This will prevent you from having bleed over between them so that you don't accidentally do something and then put it onto the wrong problem. And it is very difficult to tell when you've done that in a calculus problem. When I say don't daisy chain, what I mean is when you start to work on these problems and you have lots and lots of algebraic operations that you're doing, it's very easy to go this equals this equals this equals this, which is less than that, which is greater than this, which is equal to that. And then you have this long chain of stuff that's hard to read. Think about your work less like you're writing Shakespearean prose that is just going to be this elegant, long thing, and more like you're writing punchy comic book dialogue. Line, return, line, return. And that way it's very easy to see exactly what you've done so that if you make a mistake, you can go find it quickly. Okay? Now, define your functions clearly. As you saw when we looked at the product rule and the quotient rule, you will be breaking down big functions into smaller functions. One thing that I've seen students do is want to take that and then just immediately jump in and be like, I'm going to derive this, and then I'm going to take that, and then I'm going to derive this, and I'm going to take that, and then just start working. Pause for 3 seconds and go, hey, this is the f of x, this is what it is to start with. This is the g of x, this is what it is to start with. And that way, as you're working through, you have something that you can easily reference away from the complicated function, again, so you don't get mixed up. So that way, when you're going, I need to square this function, you can look at just that piece and you don't get it mixed up with anything else, and you can keep things straight, okay? And now, attend to notation properly. It gets very easy to want to do things like drop the word limit, or to drop a squared if you're constantly using it, not to put a set of parentheses in because, I didn't need those. The problem is that when you do those things, you might also accidentally forget that that minus sign you've been carrying around is supposed to be distributed when you're done, or that this part over here was supposed to have been multiplied through, or that that was dividing only this section of a function and not the whole thing, and then errors happen. So making sure that you are being consistent with your usage of parentheses, with where you're putting your negative signs, with all of those little things that might seem tedious and excessive, do help you so that you don't accidentally simplify something that shouldn't be simplified or forget to simplify something that should. And again, these kinds of problems get complicated, and it is difficult to just tell at a glance when you have made a mistake. And unlike when you were going through your algebra career, a lot of calculus problems are not designed to just be all like, oh, it looks very difficult, and then when you're done, you get a nice answer like X. Sometimes, especially with some of the transcendental functions, things do not simplify easily, and you will get complicated answers like 3 times the square root of the natural log of sine squared. That happens, okay? And now the last one is kind of the way that we make sure that we don't make the above mistakes, which is slow down and breathe. I know I talk fast, I'm not the best arbiter of this one, or the best example I should say. Slow is smooth, smooth is fast. What this means is that when you're working, don't think about racing a clock. Don't think about, I gotta get to the end of this, I gotta get it done fast. No. If you try to go too quickly, if you try to rush through things, you might make a mistake. And when you make a mistake, then you're going to have to go back, find the mistake, and then redo all of that work you've done, which means you've now doubled up everything you have to do. You've lost any time you thought you were gaining. Take a few extra seconds to double check things, especially if you've done something particularly difficult, and then continue on your way, okay? That few seconds of extra time will help you out. Now, let's go ahead and do a couple of the rules we learned in the last video and see about applying some of these principles so that we can see how they work. Here are the first two exercises, and there'll be two more after this, but the answers to these will show up in 3, 2, 1. How did you do? Now, in the top example, I demonstrate what I meant about daisy chaining, and it is just a little bit extreme because I obviously have chalk and a chalkboard, but this is what I mean about as you get towards the end, because of space issues, you might try to squish it in here, because I would have had to have gone down to the bottom. And while, yeah, you may not try to do this as much, you would be surprised how on tests and on homework, how often I have seen students absolutely do this while writing in pen. And by the way, the application we applied here was simply that we distributed the derivative across addition and subtraction. Okay? Now, on the next one, this is actually another principle that I didn't really discuss because this is more just something that you begin to notice as you're working with calculus, which is that sometimes it's helpful to do algebra before doing calculus as opposed to doing the algebra after. And the reason I didn't put this into the principles is because this is not as set a rule or as set a principle as the others, where you will always want to do this, because sometimes you want to do the calculus first, sometimes you'll want to do the algebra first. It really just depends on the situation. Now, on this side, I applied algebra, which allowed me to simply distribute that derivative operation across addition and subtraction. So we got through and we get to the answer of 4x minus 1. So this looks a lot like what we did up here, but you'll notice that I worked down. And it's very easy to see exactly what happened. Started here, worked to here, worked to here, got to here where I did my derivatives, got to here, got my answer. Over here, this is the part where I talk about defining my functions. So I know I'm going to be using my product rule, so I go ahead and I say my p of x is the f of x times the g of x. My first function times my second function. And in this function, it's very easy, but in one of the next ones, you'll see it's a little trickier on how those go, okay? And so I've got my f of x and my g of x, so now when I'm taking my derivatives, it's very easy to see, well, the derivative of g of x is just 2, and the derivative of f of x is just 1. So then when I plug everything in, I do the multiplication, and I end at the same answer. So let's go ahead and look at the next two problems. And here we have some that are just a little bit harder, but they are completely doable using the rules you know. Although I will warn you on the bottom one, make sure you're careful with that t minus 1 squared. You'll need to do a little bit of algebra before you take the derivative. And as usual, the answers are going to appear in 3, 2, 1. Now again, how did you do? So hopefully on the top one, that was a pretty straightforward application of the quotient rule. By defining our functions, now because we had a g of x there and an f of t on the bottom, I didn't use f and g. But again, this is one of those situations where the change of variable situation, or in this case, defining the functions, it doesn't matter what letters you use. Pick your favorite letters and just make sure you're consistent, and this is where defining those functions helps, because it doesn't matter what letters you use. Later we're going to use a thing called U and V substitution, and we use those letters because they're rarely used in words, but it's the same reason x became the math variables, because there aren't very many words that start with x that are commonly used in most languages, right? At least most languages that would have been using English letters as their variables, right? So the thing here is we say p of x is 1 plus 2x, q of x is 3 minus 4x. Set up our rule, plug in our values, hit it with some algebra, and we get our answer. Now, if you are a slightly more advanced calculus student or you've read ahead, you might have seen something called the chain rule. We'll be looking at that later, and you could have used that here. However, like many situations, if we can utilize some algebra, we can use different methods in order to solve these. And this is one of those examples where by defining our functions, we can use just our quotient rule. And we solve this by using the quotient rule again, p and x. And then when we have our q down here, I said p and x, I meant p and q. When we have our q down here, we have q as t minus 1 squared, but we can also turn that into something where when we take the derivative, we can distribute that derivative, okay? So when we do that, we take the derivative of q, and we get that the derivative of q is 2t minus 2. So that allows us to work our way through, and as you can see, things get a little complicated. This is the step where maybe you might not have solved it. I mean, I assume that you did, but if you didn't see it, that happens. Not a big deal, okay? But you can take out the t minus 1, the t minus 1, and the t minus 1 down here. And then you get down to the bottom, and we get negative t minus 1 over t minus 1 cubed. You could also pull out the negative if you don't like the negatives up there. There are some people that don't like that, just like there are some people that don't like having roots in the denominators of their fractions. I don't mind, but, you know, it's a holdover from back before we had calculators where people don't like things like that. But there you go. So the idea here is that by organizing your work, it becomes readable. By defining your functions, it helps you not make mistakes, and it helps you see methods of solving these things. So I hope that these principles will help you as we move forward, especially because next we're going to be looking at the chain rule, and then after that we're going to be looking at some of our transcendental functions. So I hope these tips help you going forward as we begin to look at more complicated functions and rules in calculus. And as usual, the answers to the additional exercises will be at the end of the outro. And if you have any questions, feel free to drop into the comments or join us on Discord.